Welcome everybody to session 06, Design Architectures at the Symposium Art Machines 2.0 in 2021. My name is Tobias Klein. I'm an associate professor here at the School of Creative Media, and I trained as an architect at UCL and the University of Applied Arts in Vienna. After that, I taught at the Architectural Association before coming here to the School of Creative Media. So I say this because it is obviously with great pleasure that I see that architecture has now, with the rise of machine learning and algorithmic architecture, evolved to a part in which hopefully we find a common ground. Hopefully this is the beginning of a lot of more exchange between creative media, art, digital artist practice and architecture. I will have to make a couple of announcements before we can start. The first one is that this session will be recorded, so as such, please be aware. The second one is to foster a culture of community. We encourage you to please keep your camera on if possible. To encourage focus, we suggest that you exit other apps and turn off notifications. Today, as in any conference setting, there may be some glitches. Please join our proceedings with patience and good humor, and we will have not glitched, but yeah. Now let's talk about the format of the session today. Presenters will speak for up to 20 minutes each. After each presentation, I will announce that the chat room is open for 1 minute. Online attendees can type your questions via the Zoom chat. The chat room will be closed after 1 minute and the next presentation will begin. After all presenters have spoken, the question and answer session will begin. I may call on an online attendee to voice a question or select a question and voice it on behalf of the attendee. And then the presenters will respond. In-person participants can simply raise their hands if they have questions, and they will be given a microphone to speak so that online participants can hear the questions. I will now give a short introduction to the first paper, and the presenter provides The first paper, titled Control and Communication, a System Study of Platform Economics and Digital Archives in Architectural Design. Based on the vastly growing digital archives, such as for instance Pinterest, being the largest architectural image vault, this paper highlights the urgency to study the benefits and limitation of digital platforms and technologies to facilitate a multi-access system for which archival functions are crucial in serving democratization in 3 ways. This paper illustrates its arguments with a speculative research design called current.cam. The paper is written by Provides trained as an architect and researcher. Her research concerns the emergence of digital tools and their impacts on architecture and urbanism. Her current research discusses how large-scale computation prompts to be a preemptive urbanism, where AI and big data are tools to simulate a parallel future that guides our design strategies. In her work, she experiments with multimedia narratives as a communication technology which expands the spectrum of architecture representation. Provides is currently a UCL PhD student. I'll hand over to Provides now. Thank you very much for joining us today, and I'm looking forward to your talk.
Thank you. Hi, everyone. My name is Provides. I'm an architect researcher. Actually, I'm currently teaching at UCL. My PhD is with Chinese University in Hong Kong. So let me share my screen. Do I need to unmute myself on Zoom? Okay, cool. Thank you. Perfect. So today I will be sharing with you my research, Control and Communication, a system study of platform economics and digital archives. So what are the roles of archives and platforms within a multi-access system? More specifically, how may such a system aggregate intelligence, both humans and machines, for the collective processing of data? So this interdisciplinary study has 4 components: an introduction to the problem space, a historiography that maps a series of events around cybernetics and its adjacent disciplines, including information and game theories, a desk review, and a speculative project, Current. So let's get started. Platform economy, what is it? It is a peer-to-peer model of circulating resources which may help to facilitate a multi-access system for the Creative Commons. Especially in the rise of generative algorithms that feed on large amounts of data, it is rapidly reconfiguring the notion of archives through democratizing the accessibility and valuation of information. Particularly, we're interested in three aspects. First, controlling communication, to which the standardization of protocol facilitate multi-access platforms and crowd contribution to a worldwide consortium of archives. Second, value circularity and information feedback. So within a platform economy, these may help to democratize the institutional model of appraisal by utilizing consensus mechanisms for self-organization and direct valuable information to users. Last but not least, something I called artificial creative common intelligence, where data archives feed into distributed production pipelines composed of various open source generative algorithms. So the question of how to take advantage of the network structure through the design of system control and communication is at the heart of the problem. Okay, that's cool. Don't worry about it. Thank you. It's working. It's working. So anyway, a systematic organization to which can be traced back to the modern history of cybernetics. Its interdisciplinary nature enables us to approach all kinds of sciences from social to natural, using a set of vocabularies that is understandable across disciplines. So basically, it facilitates communication using both natural and mathematical languages to infer models of systems and begin to work with them. Cybernetics is also one of the founding fields of artificial intelligence in its formulation of feedback, black boxes, and human-machine interactions. So usually talks on cybernetic history begin with its father, Norbert Wiener, who basically defined cybernetics as the control and communication between animals and machines. But if we're to compress time from the 40s in less than 20 minutes, would probably result in very low resolution of the research. So we will instead begin with Wiener's death. For anyone who is more interested in when Wiener was alive, feel free to visit my YouTube channel. So shortly after Wiener's death in the 60s, cybernetics saw a new wave of understanding that seeks to expand and reform the discipline, what they call a second-order cybernetics, SOC. So Wiener's cybernetic was being interpreted as first order, which is the study of observed systems, whereas second order is the study of observing system, taking into account the observer as part of the system. So the secondary concern of SOC is to proceed to construct a consensual domain as a system of beliefs. This is an idea translated from autopoietic biology to describe self-organizational ontogenetic structural coupling. So in English, it means that we can understand ourselves as individuals, be organisms or machines, amalgamate into communities by reaching structural consensus. So if we're to model consensus domain using hard sciences, we would be able to apply mathematics as a language for describing these processes. For instance, if the process of two individuals reaching an agreement through iterative exchanges can be described as changes in the frequency of signals in a time series, let's say using Fourier transform, we may write down a differential equation and map the variables within a lab setting. So as such, not only will we be able to understand the anatomy of these processes, they can now be captured computationally to preempt the outcome. For instance, automated negotiation, which basically gave birth to GANs, generative adversarial neural networks. So in Gordon Pass's contribution to Negroponte's 1970 book Architecture Machine, he tried to capture these processes with analog interfaces that generate different signals when plugged into one another. Pass was influential to the development of hypermedia as coined by Ted Nelson in 1974, to which contents can be linked to build up network connections, and this foreshadowed multi-access communal information systems of all kinds. So like hyperlink, deep link, basically they enable indexical measures on search platforms and information archives. Like PageRank, we use it every day without knowing, probably, which quantifies information value by their linkage and collaborative filtering through user interactions and feedback. So the modeling of consensual domain cannot escape the discussion of game theories, of course, which is the study of mathematical models of strategic interactions amongst rational decision makers. This has become the underlying doctrine of platform economics, where consensus is being studied with objective probabilities. So objective you can understand in economic terms as incentives. Thus, reaching consensus can be understood as reaching an equilibrium within a game, to which actors have no incentive to deviate from their chosen strategy after predicting their opponent's choices. So simply put, one has nothing to gain by changing only one's own strategy. So together with Wiener's feedback, such forms of minimax strategies are applied in all kinds of neural networks. Nowadays, most notably GANs again, which can be seen as a form of automated negotiation. So GANs are non-cooperative games, but in a cooperative game, more than often, actors do not bring the same amount of value to the overall system. Presumably, this will be reflected in the divisional payoffs within its members. Thus, we are interested in coalitional analysis, which generally concerns itself with two questions. First, which coalition makes sense to form? Second, the possibility for the coalition to redistribute the value that they've achieved amongst its members, what they call transferable utility. So these questions, when answered, define the nature and stability of the consensual domain and the participatory qualities of an information system. For instance, if you're engaged in a platform where the overall system consistently gains value, but you as the user don't get nothing back, which is what happens every day, you would probably gradually be less incentivized to contribute useful input. So much like what's happening on Pinterest nowadays, which basically degrade system functionality. By coalition, it doesn't mean that the actors' interests are always aligned, but that the coalition formed may achieve larger benefits or overcome tasks that the members otherwise could not have on their own. So equally, non-cooperative games can produce harmonious situations, an equilibrium where the overall system increases in value. So in other words, consensus domain doesn't mean we always have to agree with each other, but we can still collectively steer towards a state that is beneficial to the overall system. So basically, the past 8 minutes of content can be summarized in 4 simple Chinese characters. 求同传异. So how does it actually work in practice, right? In 2008, John Nash's late work on agency's method advanced the modeling of consensus dynamics, taking into consideration the use of autonomous agents and contemporary economics. So the control variable to the probabilities of coalitional acceptance is demand, which is presumably able to be assigned with some single value because we're in a lab setting, right? So this has design implications within platform economics, which can matchmake peer-to-peer supply and demands in that we may preempt mathematically situations or criterions that would or would not motivate individuals in the market to form and maintain coalitions so as to achieve larger payoffs. So this scientific history basically spaded the ground for scalable modeling within platform analytics, to which the study of peer-to-peer exchanges can help to reason about the larger system that emerges. So in the research, a few contemporary platform cases were reviewed in terms of 3 aspects: its network model, its economic logic, and its control and communication protocol. Subsequently, a social economic spectrum was formulated which aims at modeling system organizations. So on the economic axis, there's the copyright. So within the current system of copyright, design disciplines generally rely on information asymmetry to operate. A corresponding phenomena that we all know working in 3D is proprietary incompatibility in the softwares, which is basically a non-cooperative game. But it is non-cooperative in a way that impacts the channels to which information circulates. Thus, it impacts the forming of coalitions. At the other end of the axis, there's copyleft, the Creative Commons. It is essentially accumulating the effort of all invisible hands, as coined by Adam Smith in the 18th century. For instance, within the habitat of Wikipedia and Google, communal information environments are being set up where information is being offered to users free of monetary values. The general phenomena is that the system gains a lot of value which cannot be realized unless it populates the information environment with advertising units, a lot of ads, so they're competing for attention, or ask users to donate $1. But donation is not a realization of aggregate value, it's simply charity. On the other hand, individuals who have contributed valued information do not get appropriate returns. So this inevitably accelerates a digital communism, but one that does not redistribute value effectively within a coalition, rendering the system unsustainable in the long run. So last but not least, we have the network axes. There's centralized, decentralized, and in-between distributed organization. So we're going a bit into the technical stack. In terms of information transaction and storage, decentralization is different from distributed in that there is centrality for its graph connections. So centrality is different from centralization in that centrality is the control-based measure of the importance of a node relative to its network. So all nodes contain information for peer-to-peer authentication instead of relying on a central authority. So each point on the spectrum has its own distinct benefits and weaknesses. Our goal is a multi-access system with option dynamics, right? Which means that this spectrum should really be embedded in a spherical projection, so that every point is topologically equal in opportunity so as to maximize choices within the system. So what I would imagine as a democratic digital system, where data organizational strategies may orient itself to any point on the spherical spectrum according to the system's goals and beliefs. If we take blockchain as an example, right? Technically, it is distributed, but it is actually not inherently decentralized. So many nodes hold copies of the same ledger, but the rights of nodes to actually operate on the ledger is a different story. So decentralization is actually a question of design. So here, the research briefly summarizes a few control and communication principles. In terms of platform economies, agency's method means that harmonic system outcome enabled by both cooperative and non-cooperative actions. Consensus mechanism means to achieve equilibrium in a system within sets of peer-to-peer interactions. Option dynamics, which is the ability for individuals to describe system behavior from interacting components. In terms of formulating a participatory archive, first is discovery processes. It's basically what motivate crowd contribution through information seeding and diversifying value routes so we can escape the attention economy. Decentralized ranking, basically if you imagine Google, how can Google be decentralized? It will be decentralizing its indexing and search system within an archive so that individuals can actually realize their own value in their contribution. Last but not least is something that I call pay-per-compute. So as opposed to pay-per-click, which is pay for your attention, peer-to-peer information exchange should actually be realizing value instantly with each computational input to enable transparency between archives. So of course, this depends on the size of the transaction. If it's micro-value performed over rapid exchanges, it should really be instantaneous. So especially in digital archiving, an institutional model of appraisal may be democratized if consensus on the value of an information object can be formed based on peer-to-peer interactions. So every transaction is itself a consensus, right? Archival function is a record of all information consensus of history. So archives are different to database in that a database generally contains raw data, especially for those for unsupervised learning, but archives contain information, which involves data processing. Better yet, we're aiming for collective processing. That's decentralization, right? So in fact, this is not so different to how art specialists authenticate a painting, partly by the labels on its back, which documents all of transaction history. Generally, the more time you trade something, the higher the aggregate demand, the higher the recognition, and the higher the value, right? So for instance, NFT, non-fungible tokens, everybody's talking about it nowadays. The interesting thing is that it is actually placing stewardship over ownership, even though it's pretending that it's operating on ownership. So as opposed to you owning a physical art object, you actually have a label that tells everybody that you have the right to a digital artwork. So that's basically mirroring what's happening in our attention economy today. So these case studies led to a reflection on the design research. Looking back, I'll say that me and my collaborators, we're trying to delineate a future of copyleft decentralized system, which is multi-accessible, aggregating intelligence of all invisible hands, where platforms and archives are tools that channel participation and consensus through feedback, except we ask the question, where should the attention value generated in our attention economy actually go? So that's the important question that everybody should ask. So the Project Current is a speculative project that thinks about the future of broadcasting cinema facilitated by participatory urban archives. So Current questions the authentication of truth through the crowd contribution of multiple point of views. Imagine a chain of cameras forming blocks that authenticate each other, which enable us to volumetrically reconstruct contested events collectively, a blockchain camera. So the quality of collective processing highlights the significance of archiving. The question of how we can facilitate an artificial creative common intelligence is at the forefront. This points to a new form of creativity where the authorship is a participatory one and contextualized the relationship between AI and creativity in the Creative Commons. So the word creativity in the 19th century embedded itself in poetry, science, and art, not merely a form of repetition and propagation, but a creativity that reconciles with rules, a consistent construction, deconstruction, and reconstruction of boundaries. In current, reconstruction is how pieces of information objects come together, resolving the edge of content, which is essentially information consensus. As opposed to the conventional view of consensus killing creativity, consensus actually constitutes creativity. Of course, creativity has encountered an archetypical turn in the face of AI, which can take forms of rule-based and machine learning systems. The former involves the design of models with sets of rules. The latter achieve intelligence with machines that define their own rules based on available data. So this transcends creativity from causation to correlations, from small to big data, from databases to archives. Such a probabilistic approach implies a measure of the amount of possible arrangements within a state of a system, a measure of entropy based on control and communication. If we're to contextualize entropy within the art of design that is bounded by our social economic demands, it implies a cognition beyond the past and present state of a system. Entropy seems to capture the critical information that we need in order to speculate on the future evolution of a system. So such measures are made available through crowdsourcing discovery processes, where not only data is aggregated, but also computational power for the collective processing of an ever-mounting terabytes of data. What interests us in this project is the role of AI in information reconstruction as a form of consensus. So alongside the cinema, Karen experimented firsthand with a range of rule-based and machine learning systems that are readily available to any individuals, and we developed distributive pipelines feeding off open source archives, which provide a means for individuals to collectively reconstruct, navigate, and understand event landscapes that are often hidden from us, such as changes in polar bear behaviors and so on. In this process of iterative feedback, filling in voice between sensory data into an endless stream of his story, where crowd contribution and algorithmic generation come together as a larger whole, this is how Karen defines artificial creative common intelligence. So this can facilitate an attention economy that direct value back to the entity of reconstruction, harnessing network effects for the protection of such entities via micro-licensing and virtual signaling. This is where blockchain may become handy because it can automate peer-to-peer transactions, facilitating value routes for each reconstructed data points to be streamed and minted as NFTs or not as NFTs. This enabled endangered landscapes to own themselves by crowdsourcing awareness and contribution, incentivizing a social economy to form around a post-human system. So currently, Karen is working on testing the limits to volumetric livestream that updates the simulated environments in near real time. Of course, this is also the job of big companies like NVIDIA, so we're more focused on distributed pipeline using lower-end technologies that's readily available to even you and me. So our work in progress is being exhibited as a 12-minute cinema also in this conference. Welcome to see it and watch the whole film. This is like only 3 minutes of the film. So the consistent effort should not be credited to Karen alone, but also our international network of talents. We always welcome anyone who wishes to collaborate. You can get in touch with us or get in touch with me via my Instagram, provids.ism. So thank you for your attention. I hope you enjoyed the talk. If you wish to join our conversation, there's a roundtable series that I've been organizing at UCL. It's open for all. Everyone is welcome to join us, and you can find it on the UCL event page. Thank you.
Thank you very much, Provides. We now have a 1-minute break in which we welcome anybody to write down their questions in the Zoom chat. And we will then continue with the presentation of Alessio Erioli and Alessandro Mintrone. Welcome to the questions and explanations. Great. So the Q&A is now closed, and we are continuing with the contribution of Alessandro Mintrone and Alessio Erioli. Cognitive assemblages are spatial generations through wave function collapse and reinforcement learning. The research explores the integration of AI in an iterative decision process for the open-ended procedural generation of architectural spaces. Leveraging on state-of-the-art deep reinforcement learning techniques, an artificial neural network is trained to perform local decisions selecting tiles in wave function collapse algorithm, assembling discrete elements that build up a complex spatial organization, pursuing selected spatial qualities at the architectural scale. The presenter is Alessandro Mintrone. He's based in Bologna, Italy, and is a computational designer, architect, and engineer. Graduated from the University of Bologna and working both on design and research. In his work, he explores artificial cognition, simulation, machinic fabrication, and tries to investigate the porous zone of human and non-human collaboration from which new ideas of architecture can emerge. He is working together with Alessio Erioli, a University of Bologna Professore Aggregato, which is a teaching professor, co-founder and designer of the famous Code DIT, and researches the aesthetics and tectonics that emerge as a consequence of computation in architecture and related fields, focusing on intelligence in the process design. He's also skilled in computational design, programming, modeling, which is highly, highly valuable these days. So, welcome and thank you very much for your contribution. I think, Alessandro, you wanted to present?
Yeah, sure. So, wait a second. Okay. Hello and welcome. This is Cognitive Assemblages, and of course this research focuses on the integration of AI in this iterative decision process. And basically our goal is to achieve those three-dimensional assemblages while pursuing specific yet computable spatial qualities. And in order to do so, we leverage on two different systems. On one hand, wave function collapse algorithm, a pretty well-known in the gaming industry iterative and content-based generative algorithm that follow specific constraints. And on the other hand, reinforcement learning techniques that train a artificial neural network to perform local selection and build up those complex spatial structures, while at the same time finding way to orient in this complex but quantifiable landscape of possible outcomes. So, as we see every day, AI is gaining traction in a lot of different fields. But when it comes to architecture and design, we are facing a few hindrances at a time. On one hand, many possible systems produce self-sufficient, complete outcomes that are basically black boxes obscured to the intervention of a human designer, and at the same time they do not provide opportunities for the free flowing of information between both sides. On the other hand, many other solutions provide just vague references to the architectural content, just imbued with a small amount of architectural information. They provide generally images that need a human intervention for being interpreted and translated into an architectural form, restaging the old and at this point trite myth of the creation as a sudden intuition translated into reality, or the imposition of a preconceived ideal over a helpless matter. On the other hand, we try to question the very concept of authorship and instrument altogether. And by doing so, we envision the act of thinking as a diffuse, granular, and embedded act in an ecology of cognition capable, possibly, of extending and reshaping our mental territory. Long story short, our idea is that both human agents and those complex cognitive machines should be part of a network where both the nodes and connections are equally important. And at the same time, we envision those tools as liberated tools, not just the reflection of the user's mind or just poised to parrot human thinking, but we see those tools as able to develop their own sensibilities, their own biases, their own directions, and to guide this process where the authorship is no more concentrated in just one point of the process, but is diffused and continuously negotiated. In order to do so, we need a common language, some way to exchange this information, some way to also store a common way for human to think architecture and for machine to understand it, and of course computed. And when we were finding a way to do so, we fall into wave function collapse algorithm. As I stated before, it's pretty well known, especially in the gaming industry, and is a constraint solving algorithm that provided a set of discrete elements, a discretized representation of space, and at the same time some connectivity rules, is able to assemble those elements into this discretized representation of space that in our case is a voxel grid. It does so based on an entropy analysis, and the definition of entropy is generally the Shannon's one, so it's just computing the Shannon entropy. And this is the key point of this algorithm, because by analyzing the entropy is able to select the point where there is the least uncertainty, the least level of uncertainty among every other points. In this way, by selecting that point and placing a tile and discrete element in that point, collapsing, because of course this process is largely reference to quantum mechanics, and this is the jargon that is used in this process. By collapsing, by placing those tiles in those specific points, we are assured that we lose the minimum amount possible of information, and this is very helpful when the aggregation grows, because it assures that the aggregation will maintain some global properties without falling into contradictions. And of course, after every iteration, this information is diffused. Let's see in a moment some more minute details. We provide single tiles with their geometry and connectivity rules. We provide rules for geometrical permutations based on, of course, their geometry. And we provide the rules for the possible connections and the forbidden ones. When the algorithm cannot place any tile in a specific point while following all those constraints, it's said that it falls into contradiction. Otherwise, the assemblage complete the entire grid. And as you can see here, we place the first element, and then the information is spread throughout the grid until, of course, the aggregation is completed. As we can see in those three-dimensional examples here, stemming from a very simple and limited set of tiles, 5 in this case, we can achieve a vast and complex level of spatial qualities and spatial properties at both the local and the global scale. And as you can see here, just changing the geometry or the connectivity rules, we can afford a vast amount of possible spatial outcomes. But, of course, this system shows some hindrances, especially from the fact that it's pretty homogeneous and there is a lot of self-similarity. This is due to the fact that every tile is selected out of pure randomness, provided the point where the tile should be placed and provided all the constraints. And for this reason, we bind it with reinforcement learning, precisely because in this way we can steer the aggregation toward specific spatial qualities that we will see a bit later. And as a general framework, reinforcement learning is based on an agent that receive information about the environment, provides an action, and this action changing the environment changes its state that will be re-entered into the system for the next iteration, and the agent will of course perform the next action based on this changed environment. While we are training, another layer of information is provided to the agent, and this information is called reward. Basically, the entire training process is going toward maximizing the reward, finding a specific behavior from the agent that is capable of maximizing the reward inside this environment. And of course, a famous example is AlphaGo, and the first software able to beat a master in the game of Go. And this is pretty interesting because differently from other systems like GANs especially, or other based on a data set. In this case, there is no data set, there is just the environment and some rules, and the system is able to come up with an expected solution that stems from the rules and the definition of what is a reward and what is not, but maybe are obscured at our site. And structurally, basically, we by the neural network to perform the tile selection. So the point is which tiles place is selected in the usual way, but the neural network decides what kind of tile should be placed there in order to achieve those specific spatial qualities. And in order to do so, of course, we need to provide some reward to say what is good, what is not. And in order to do so, we need to define, to quantify, and making computable the space. And we provide 6 quantified spatial descriptors that are both local and global. And they are density, that of course is pretty self-explanatory, a gradient, that is the spatial distribution of density, the global average orientation, structural connectivity, spatial connectivity, and planar connectivity, that of course accounts for the orientation of the planes and of course makes sense only in three-dimensional assemblages. For every single spatial quality, the reward is not provided as an ideal level that should be optimized, but on the other hand is provided as a goal ever changing, and maybe the neural network should achieve a specific density now and another specific density in the next iteration. In this way, what we achieve is not just an optimization that follows our preconceived idea of what is a good architecture, but a complete mapping of what is possible to achieve within the design space provided by the designer in form of those components and connectivity rules. As you can see, and this is pretty common for reinforcement learning, the neural network is pretty simple, just 3 layers comprising 256 units each. And this entire neural network is based on machine learning ML agents library within Unity, that is a reinforcement learning library based on TensorFlow or PyTorch, and able to visualize the outputs in TensorBoard. And this is pretty interesting because we compare the results of the trained neural network with a probabilistic heuristic that instead just assigned different weights to every tile in order to try to achieve a specific goal. In this case, the goal was to achieve a specific density, 50%. And as you can see, not only the neural network performs better in a quantifiable term, but at the same time, it provides some global pattern that really emerge from some kind of strategy. Basically, what is learned is a specific behavior that try to achieve a specific goal. And by iterating over and over this behavior, you see that there are some clear pattern, and this can be called some global level of organization or strategy, if you do prefer. And as you can see, we can look at some example. In this case, we started with just one specific quality at the time. In this case, density. In this case, orientation, providing from time to time different goals like diagonal or horizontal or vertical, or no orientation at all, connectivity, and so on and so forth. Then we started mixing two different qualities and trying to find a balance between the two of them. And as you can see, of course, the more qualities, the more pressure, the more evolutionary pressure, the more complex and stratified the outcomes became. And in those examples, we have all the different parameters acting at the same time. Okay, now moving from those 2D experiments to the three-dimensional representation and to more architectural issues, we reasoned about the very concept of assemblages, a concept, of course, issued in the first place by Deleuze and Guattari. And basically, the main point is that we are trying to redefine the very concept of assembling element into the architectural realm. As you can see, assembling predetermined elements is not new into the architectural domain. It's something that we envisioned even in the 60s, like in this example from Moshe Safdie. But as you can see, those elements are pretty specific, have predetermined function, have a predetermined organization and arrangement. What we envision is the exact contrary, in which every element is as generic as possible and can perform different function and can generate different spatial affordances without being binded to a specific role, but ever changing its possible outcomes. And as you can see, for this reason, we selected just the simplest possible tile set for our two-dimensional exploration, just simple planes with simple connectivity rules, just 6 of them. And as you can see, when we start exploring this pretty vast array of possible outcomes, one thing is clear, that it's pretty difficult for our mind, for our cognitive abilities, to make sense of all this complexity, especially counting that those three-dimensional elements are more difficult to inspect than their bidimensional counterpart. And for this reason, we try to develop a system of orientation in this space. On one level, there are those 6 quantified spatial descriptors that provide a map for this 6-dimensional space. And at the same time, we developed a visualization system that, of course, accounts for many spatial qualities like density, connectivity, and of course, autonomously generates some view in order to have a as complete as possible representation. But the main issue here is that since the entire database that we generated, like 10,000 possible designs, since this database is computable, we cannot refrain from expanding over and over the possible ways in which we can ask questions to this database. And this is precisely the point. When we translate the information in a way that is computable for machines and understandable for human agents and designers, in this way we afford a new feedback loop-based system of communication and interaction and use of instrument, in which both authorship and agency are diffused and are distributed inside the system. And in this way, we hope to achieve some level of cognition that is not possible nor for human nor for machines alone, but is only possible when the two are connected in an ecology of cognition that hopefully extend beyond the reach of both cognitive capabilities. And yeah, this is Cognitive Assemblages. Thank you for your time.
Thank you very much. We now open again the chat for 1 minute for any questions that we will then have in the Q&A session after the third presentation. Didn't show up. Okay, the Q&A session for the writing is now closed. We will continue now with the third and last presentation today. Unfortunately, the second presentation by Karolína, Kotnour and Robert B. Lisek did not happen because the presenters were not online. The final presentation is by a newly founded architectural initiative called Rational Energy Architect, founded by Baha, Odaibat, Doria, and provides... The paper is about translates informational biological principles into the design of architecture, and more specifically reviews the use of Gestalt approach and free energy principles in biodesigns, to ask how can artificial intelligence or AI systems learn from biointelligence to facilitate designs that are sustainable and aesthetically interesting. The research illustrates its argument with a design experiment, the Unattended Solar Energy Smart Urban System, and as that is a very long title, it has been abbreviated to UnSESUS or UnSESUS, and well, UnSESUS. So I'm very happy to have provide again speaking to us, and I don't see actually your partners online at the moment, but maybe they join as well.
Hi everyone. Hi, yeah. Hi everyone, it's me again. I'm Provides, but now we're the Rational Energy Architects at REAR. So my collaborators, Baha, David, and Bertel. Thank you, Tobias, for introducing. Our interdisciplinary research focus on rationalizing energy use and its application in design at the scale of architecture and urban. So today we will be discussing with you an information theory approach to biodesign architecture. We asked the question, how can artificial intelligence learn from biointelligence to facilitate designs that are sustainable and aesthetically interesting? So here is our golden triangle with 3 core ideas. First, solar design. Second, bio-inspired form finding. And third, human-machine interaction. So we're looking for what can possibly happen in between, comprehending our natural and built environments, which are complex and chaotic in nature. We focus not on an optimal output, but systems that optimize variational outputs for diverse applications. So I'll be introducing the theoretical approaches, then David will explain our combinatorial pipeline that synthesizes rule-based and machine learning system. Finally, Baha will be discussing the mathematical principles behind the proposed solar installation. So in solar design, we focused on integrating parameters of smart material properties, such as emerging thin film technologies and perovskites, with self-organizational approaches. So as inspired by nature, a system that is adaptive and efficient within the Earth's energy environment, self-organization is sustained through the rapid feedback of all sorts of information, from DNA to natural languages. So even though the word information is a noun, in fact, it is a process, a construct that arises in the process of trying to understand our complex environment. So within the context of solar design, how should we create information? What kind of information are we looking for? Is it patterns extracted from stochasticity? Most importantly, how do we understand and make use of information entropy within design, and how do we relate that to energy entropy? So in raising these questions, this research rethinks the relationship between information, biology, and intelligence. Based on the neuroscience free energy principle, active inference is what intersects between infobiology and AI. It is how individuals, be it living beings or machines, use an internal generative model to predict incoming sensory data, so as to minimize variational free energy, which is the minimization of local or internal entropy of a system. So one such example is the Markov blanket in a Bayesian network, which is commonly used in predicting probabilistic relationships by minimizing information entropy. So this helps us to better understand artificial intelligence as a tool for design, from generative algorithms to predictive analysis. For the former, we focus on using rule-based system for Bao-inspired form finding. For the latter, we focus on helping machines to learn within a solar environment. So since all of these algorithms are weak AI that focus on narrow tasks, the understanding of which intelligence is better at what task and which algorithm has the potential to be accelerated with machine learning is critical. So we formulated various combinatorial pipelines that integrate rule-based AI, machine learning, and design intelligence, a human-machine interaction. So this research illustrates its argument with a design experiment, unattended and smart solar energy urban system. So I will explain it word by word. Unattended, meaning that the system can be left unattended by human agency or external power source through being smart. So smart refers to a system that has sensory, actuation, and control units to self-organize. So this is also where artificial intelligence can be useful. The system will be focusing on urban context to compensate for our modest renewable energy capacity in cities. So this can help to minimize energy entropy by eliminating the need to transport energy from very far locations. Also, this reduces the need for being in direct competition with vegetation and our natural surroundings. Like this, we're removing trees to plant solar farms. So overall, the system aims at tackling 3 issues. First is to distribute infrastructural power using information feedback, because not every architecture has the same solar capacity. This is because of natural and artificial parameters such as factors of incoming light, users' energy demand, and so on, where information feedback provide a holistic approach to balancing energy supply and demands. So second is that we have to leverage between aesthetic, microclimatic, and structural concerns within design. And third, we have to minimize energy dispersal, i.e. we have to minimize local entropy through active inference. So in the system, the minimizing of energy dispersal is achieved through negative entropy, what we call negentropic design, where a solar swarm installation is proposed based on the Hadley cell, which transport energy polewards for more equal distribution. Baha will be discussing this with you in more details.
I will be talking about the value of boundaries as integrative topological structures. The built environment is defined by a hierarchy of sub-environments as objects, with rigid projection on socioeconomic value and stakeholders' characteristics. The boundaries of these objects increase in complexity and decrease in efficiency as well as in value over time, with the risk for the built environment to become an eclectic frozen mess, where in contrast the socioeconomic context is far more dynamic. To jumpstart a shift in inhabited structures, a 2-part investigation is required. First is the shift in object definition, redefining the boundaries as the new objects, for they do not only inherit the differences between the bound environments, but also the relationship between them, therefore inheriting the DNA of their multiple typologies. Second is the value-defining process of those boundaries, to place a price tag on their flexibility and integration over time. through the investigation of the iterative three-dimensional information as surfacing model and the geometric understanding of their energy tessellation in the mathematical field of dynamical systems. Strange attractors are the spatial collective iterations of multiple initial conditions of a chaotic system. The fact of being chaotic suggests an indeterministic quality, although that is true locally, yet it's stable globally, with a typology that could be rationalized. The solar swarm is an attempt on rationalizing the global geometry of a chaotic system through ensuring the developability of the surfaces. The surfaces are made of an orthogonal unified subdivision due to the solar panel tessellation technology, hence the straight bands principle. With the help of carbon nanotubes technology, it is possible to actively bend the bands into the global geometry needed. In turn, the swarm is encapsulating the potential projections of solar conditions that could morph and reintegrate in multiple dynamic environments.
Thank you, Baha. So basically, negentropic design is equally important for the information that represents energy exchanges so as to minimize uncertainty and maximize efficiency. So by applying active inference through AI, we aim at facilitating a smart energy installation that is not reactive, but preemptive. So basically, it's going to act before energy demands and climatic conditions are realized. The immediate advantage is that a reduction in energy absorption by the power grid, which is usually obtained from carbon fossils. Thus, it's going to be environmentally friendly. Our methodology is to couple the Baha-inspired form finding with a personalization feedback system. So we started with a Sudoku gameplay to rationalize information feedback, which is a combinatorial game that acts as a distribution strategy to resolve the hierarchical structure in time and demand factors for solar energy. So each box in a Sudoku can be taken volumetrically as a voxel, and each voxel can be embedded with user and energy data for personalization. This brings together user and the solar installations, facilitating information feedback between a network of humans and machines. Based on these results, our research has made new progress in exploring how such principles can be accelerated with artificial intelligence for design production, and the use of voxel data points as geometry proxies for more complex Baha-inspired forms. So as opposed to using Sudoku as a distributive strategy to create a bias that influences the voxel data, we used an aggregative strategy for design production. As you can see from that feedback loop right at the middle, which helps the AI to learn within a solar environment, this loop is how the rule-based system encodes designer input and solar optimization with visual algorithms. So going through parametric means, cellular automata, and genetic algorithm, the rule-based system is going to teach the machine learning to learn within a solar environment. So this helps to minimize human labor in the training process within supervised learning. And after the machine learning model is trained, this kind of automation not only relieves the heavy computation from the rule-based side, it basically proposes a means of how various intelligence can come to consensus from designer intuition to algorithm generation. So through developing a critical understanding of what computational intelligences are modeling behind, from artificial to natural processes, David is going to introduce in more depth.
What is artificial intelligence? So by the book, AI is a scientific field that studies the development of algorithms that solve problems that are usually associated with intellectual labor. But you need to keep in mind that this is not necessarily accomplished by imitating what humans would do. It is developed through the ability of machines to artificially reason over data sets and complex questions. Cool, but what about machine learning? What is machine learning? So machine learning is the study of computer algorithms that are not explicitly programmed to do a task, but learn how to do it and improve automatically through experience and using data samples to learn from. To go into the examples, we're going to talk about three main types of approaches to machine learning. Here we have our example, which is a project that uses a combinatorial agent. If we're thinking about geometry, if we're thinking about our architecture, this project uses a combinatorial agent that tries to fill this voxel grid with these components until the grid is filled to a target capacity, to a target point ratio. This algorithm was trained by these two image pairs in which you like the configuration, just the black elements, and I want the algorithm to draw me these red lines, and that was it. And in order to do that, with the components in, I translated the voxel space into pixels, so we have the components against the white That was the image that you were seeing before. That was supposed to be fed into Pix2Pix to generate the red lines. And then algorithmically, it's quite easy. Just remove the red lines and you have the spaces. And this is a sample of the training set that I had to develop. So it was a bit over 2,000 image pairs. And I had to draw them by hand, right? And I needed to go through this process because I needed to embed my bias of feeding what is the space to an algorithm, an extensive process by the end of the day. So you can see here some samples that have been generated by Pix2Pix. And this brings us to another example. Pix2Pix is cool. You can do machine learning with it, but it is too deep. Right? And it is a big problem for machine learning and architecture right now, because most of the applications, if not all of them by this point, are based on 2D. I know I showed the reinforcement learning example that had the agents navigating in 3D, but most of the applications are based on 2D, on images. And one of the biggest problems is just computational power. It's really hard to process 3D data as we process other types of data that we're using right now in machine learning. But what we're looking into right now is how can we use a process that we know it works, it does what we want it to do, and make it 3D. So this exercise that you're seeing right here, it is a 3D-ish example of machine learning using Pix2Pix. So what we did, we were trying to embed gesture bias. When you present something, let's say a drawing to someone, and it has 2 points, and you ask this person to make connections between those points, what we wanted to do was to embed the biases, the intuition that the person as a designer at that stage would use to make those connections and use that to create 3D shapes with it. So what we're doing right here is, again, we have a voxel grid, so we have this stack of voxels, and every horizontal layer generates an image. So when I'm drawing here, all of these black structures are segmented by layer, and we feed that into Pix2Pix, and we get an output from it. And the output that we get are these connections that we see right here that are being informed by the way that the person that was drawing would make connections based on the training set that we had developed to train the Pix2Pix algorithm. So that's why it is 3D-ish. It's not really 3D. We're using stacked images, but that's how we're doing it. And just to wrap it up, this brings us to our pipeline that we are developing. What we want to do is we will start from a local context, and we would use this data, the location data, with the solar data that is associated with this geographical location to do a solar radiation analysis. The other part is that we'll be using a mathematical model to create a geometrical shape, or better, to create a geometric shape generation strategy, in other words, an algorithm by which you generate stuff, on which you'll be doing an aggregation using MOS, using discrete elements, combining those two with the solar radiation analysis to feeding to a genetic algorithm that would generate you a final form, a resulting aggregation. In other words, trying to blend in the designer intuition and intention that will go into the definition of our mathematical model and the aggregation. Remember, we're using biases to our advantage, and we would use the machine analysis through Ladybug and through solar radiation analysis to feed into a genetic algorithm to find a best solution for that problem in particular. This is a process that you will see is super intensive computationally. It's super expensive computationally. And it would take hours and hours and hours to find a solution. So what we're thinking about is how can we use Pix2Pix to automate this process, to take this huge analysis and compress it into an algorithm that can run almost instantaneously. And to do that, we would take our location and context to produce an image, and we take our final resulting aggregation to produce an image and train them together into Pix2Pix and see what comes out of it. Then do that to automate this process. So it is basically what we're doing is the automation of design, automation of analysis, and automation of the final optimization of the design.
Yeah, sorry, David was basically attending from my YouTube channel. So the whole story is basically, instead of David being slaved for the machine learning, now we slave the cellular automata to output the 2000 image data set instead. So we're carrying the aggregation strategy from the designer all the way to cellular automata, all the way to Pix2Pix. So our team is very dedicated to sharing knowledge. We have been teaching several workshops at conferences with the pipeline, and this web VR holds some results from our brilliant participants. In this virtually difficult time, we keep testing and iterating the pipeline that produces not final designs, but the participants' own critical variations of the pipeline. Thus, that's what it meant by combinatorial. So they can bring home with them the capacity to continuously design for diverse solar environments, seeking to enhance our modest renewable energy capacities in cities via photovoltaic elements aggregation. So if you're interested to know more, welcome to join our virtual exhibition or future workshops. Our next one is actually going to be with Digital Future in a month's time. So more information on our Instagram page. Thank you so much for your attention.
Thank you very much. This concludes the session of talks. We will now open again the chat for a minute for further questions before we start the question and answer session. Right, so the question Q&A session on the Zoom is now closed, and we're going to the Q&A session now. We can start the session with the question posed by Hector Rodriguez. Hector, are you still online? Would you like to pose your question yourself, or shall I read it? I can read it, of course, Hector.
You're shy. You're not
see
shy.
That.
Come join us.
So Hector asked the question about where provides has considered the critiques of game theory, for instance, by Varoufakis and others, and why does she rely on game theory? Right, I'll pass over to you in this question.
Yes, definitely very challenging question. I guess one of the limits I find to game theory is that first, it's in a lab setting. That's why I keep repeating it's in a lab setting. And second, it's hypothesizing that every decision maker within the game is rational. So within a real market, of course, like I don't do rational decision on a day-to-day basis. But I think it's interesting for machine learning because autonomous agents can be rational almost every time. I think it's every time. When I try to play Go with my computer, I never win because it never makes mistake. It only play like less challenging moves. So I think I go back a lot to cybernetics and game theory because of the trend in machine learning. And I feel like there are a lot of disciplines that actually might provide a more refreshing perspective in how we can think about these intelligences. Thus, I rely part of my theory on game theory. But in terms of real free markets with real human agents, I do agree that it's quite a limiting perspective. And for instance, Rodriguez also mentions situationists, which might be more humane in a way, but it's still free market.
Okay, Rodrigo, not Rodrigo, sorry, Hector, any follow-up?
Yeah. So. As socialist, yeah, really? Okay, interesting. Because it's like, I buy, therefore I am. It's more like a critical project based on a free market. I would say Pokemon Go is situationist in digital format. Council communist. Yeah, we should debate over that sometimes, but I don't want to take over all the screen time.
Yes, I was actually thinking as well about Guy Debord when this came up, and I cannot see that either as a market part as you described it.
What I understand, it's like you can place markers within a built environment, and that might actually intervene with or influences user behavior. So, yeah, maybe my understanding is more personal, but that's how I would see in operation within today's. Maybe I'm pre-influenced by today's society.
Okay. Now I have another question actually to provide before we move on, and you started your presentation with a fairly fast but elaborate review of the cybernetics, and I'm wondering, while that was enlightening and quite wonderful, how does this actually really fit into your project? And then how, in the end, when you make claims of, let's say, landscapes to own themselves, how that actually plays out? Because I found this claim very exciting, but I cannot follow up how this actually makes sense, or how this comes together from the initial outline that you give.
Yeah, very, very, very insightful sets of questions. It's always what I'm asking myself. How does cybernetics fit into the actual output? I mean, originally, I think I probably, because of time, I skipped to one part in between, which is the part that talks about blockchain and a cybernetic influence on blockchain that actually emerges in 2008. Like, why at that time? It's because of after the dot-com crash, people realized that one-way communication actually cannot sustain an economy big enough to not crash and not bubble. So I'm not sure if that actually ties better the different parts, but I do agree that there's a gap in between which has to be filled. In terms of the landscape that own themselves, again, it's a question that we're also asking. We have thought about different ways. Like, for instance, can we have an algorithm that is calculated, let's say, based on the size of the forest? So it's negative value circulation. Every time the forest minimizes in size, your coin actually drops, or the forest maximizes in size, your coin also rises. But then ultimately, we think it's more about how the information raises awareness and behavioral change. Because, for instance, if we're talking about plastics, we're not going to have a Bitcoin on every plastics and then we stream that on an internet and pretend someone's going to look at it. But it's more like, how do we tie a more permanent social value to an object? So that's the claim about landscapes that own themselves. It's like when my grandparents told me when they were very little as a child in Hong Kong, and then it was so poor, plastic was so rare. When they found a plastic, they wouldn't throw it away because it's such a precious object. So I guess it's more like it should be a social economic intervention rather than a technological oriented intervention. Nonetheless, I think cybernetics actually has the capacity for us to comprehend both social economy from managerial cybernetics to actual technology of feedbacks.
Okay. I'm actually being very rude because I haven't asked if there's any questions in the audience. Yes, and I did think so that my dear colleague Ray LC has a question. Could we get the microphone to Ray?
Hi. Thank you. My question is for the Cognitive Assemblages group. Alessandro, very interesting talk. Thank you for that. I'm just curious about what exactly is the reward strategy for the reinforcement learning? I think you talked about how it's kind of parameterized somehow a little bit. I'm just curious if you can give us a little bit more detail about how the reinforcement learning and what exactly they're optimizing when you create those assemblages. That's the first question. Should I ask the second question now, or should I wait? to ask later. Let me just say the other question, because it's very simple, hopefully. The other question was, have you thought about some sort of multi-level structures and how they might fit into the cellular assemblages model? What I'm thinking is something like elevators, right? Which you generated these really beautiful networks and building examples. I wonder if something like that is also can be incorporated into that model. Thank you.
Okay, I think I'll go. And basically, the main concept is that we are not optimizing a specific quality inside our training, but instead we are teaching to the algorithm how to explore the space of possible outcomes. Long story short, we provide at every iteration a number of qualities, like just one quality or multiple qualities. Let's just say that we provide density. At every game, at every iteration, we provide a different density goal, like 50%, 75%, and the algorithm is provided also with knowledge of the current state, the current density. So it knows that there is this goal, 50%, and the actual state is 75, let's say, and it also knows what's happening in its surroundings in terms of other tiles. And in this way, it has to find a way to achieve that 50%. Now, since we change the goal every time, the algorithm is not just trying to achieve a preconceived perfect level of density or any other parameter, but is learning how to achieve every possible level of density inside, of course, the boundaries that we provided, that are, of course, due to the design of tiles and their relationships. And this happens for every other parameter. Of course, we need weights and balances to connect multiple goals at the same time, but that's the basic strategy. We train the neural network to achieve every possible state inside the design space, and we then use that knowledge inside the neural network to explore those possible designs. And of course, it's pretty tricky when the number of goals start rising, but we think that this is a lot better than just optimize for a specific value. And for the other question, the elevator related question, well, there are two ways to expand on this system. You can either assign new goals to the neural network, or, and this is pretty valuable, you can provide other constraints to the assemblage system, the wave function collapse system. And for your question, we think that probably it's better to provide other tiles that can perform other relationships, that can provide other spatial affordances like elevators in a sense, and then let the neural network, the reinforcement learning algorithm, free to explore those possibilities and maybe discard them or support them or use them, coming up with novel ways we never have come up with. Did you want to expand on that, Alessio? Or we're fine?
Well, you basically covered all the points. I just wanted to add a couple of things. One thing is that while we started with the wave function collapse, we are not particularly attached to that as a generation system. So it's more important that we get to a point where we define certain actions that we can then train through reinforcement learning. And those actions are actually assembling parts that contain things at the spatial level, and then they create more extended spatial conditions. So elevators are actually absolutely possible, both in the wave function collapse framework or in other more general frameworks of assemblage of discrete parts. It's just a matter of putting the right constraints. About the first questions, the reward system, yes, Alessandro said it pretty clearly, but the idea about the reinforcement learning is that the goal is not a specific situation, rather the capacity to perform a specific task, which generalize a little more the fact that, okay, the task is to reach a target density, for example, whatever the target is. And not, so it doesn't frame things into a pretty, let's say, particular condition, but all the possible condition that falls into a more general scenario.
Thank you. I want to play devil's advocate here for a moment and recall a lecture about almost 20 years ago that I was participating as a student at the Architectural Association, in which I remember Mike Weinstock and Carl Schuh talking quite clearly about genetic algorithms, performance and fitness criteria sorting, and the rerunning of that. So this is a debate which looked visually very close to what you presented today. Of course, it is not the same, but could you explain maybe what has moved on in 20 years about actually how geometrical iterations and the sorting and performance criteria have evolved? Devil's advocate question, I have to... that goes to, of course, Alessandro and...
to us, not generally...
Yes, I mean, I was thinking about
okay, no, then...
of course, there is some part of that question that would go maybe as well to the presenter.
Of course. I have generally... By the way, Karchu was one of my teachers when I did master's, so...
I did not know.
I know what he's talking about. I think I know what he's talking about pretty well. In terms of fitness and performance, I have to say that I am one of those who are pretty critical about the use of genetic algorithm and optimization when it comes to optimizing a global, let's say, a global object. I design an object and then I use genetic algorithms. I did several experience with single objective, multi-objective optimization. The point is that optimization works when you frame a problem that admits that solution, but not in a more complex scenario where there is no definition of a possible solution. I think what changed, or at least what's our intention, is to move that kind of optimization process from a goal-oriented scenario, like global goal-oriented scenario, to something that is more granular, distributed, and embedded into the action itself. So single actions that are trying to let's say, be more close to what was the original formulation of the principle of minimal effort. That was not just to minimize for the sake of minimizing, but minimizing to maximize some sort of output, but it's not just a single thing. That could mean an overabundance of characteristics that are also beyond the control. So you have, for example, there are examples in biology of spiders that are putting almost all of their energy at the risk of their own lives to build webs just to capture bigger birds, for example. That's one thing that intends this kind of optimization scenario in a better framework for us, which is okay, I am putting this for a larger objective, but that doesn't mean that I minimize my effort or I build the minimum effort thing, but it's just something more complex. Or as I like to say, sometimes optimization, I intend it as how would you optimize the words in poetry for maximum effect. So there is this kind of work by a poet that optimizes words in a poetry, but that's the kind of optimization I like to think about when I work on this kind of research. I don't know if Alessandro wants to add something to the question. That should be the answer.
Alessandro, do you want?
Maybe I can try and add something. I actually really admire their project in that I guess it has a very similar attitude in that it's trying to measure the possible amount of arrangements in a system with a take on entropy, which I think I'll go back to that later. But in terms of what has progressed from genetic algorithm, I guess I can't give an answer as specific, but I think overall in fields of biology, I think it has progressed from a biology of things to biology of processes. So it focuses more on actually the exchanges between individual entities. Like the two theories that we based our project on, for instance, the free energy principle, I guess how it has differed progress from the age of GA is basically it talks about one step more, like how you use an internal generative model to predict incoming sensory data. So it's basically saying that, very simple example, if you feel thirsty, you would imagine that you drink some water and then you feel like it's a desirable state. That's why you go and drink some water. So that's like a hidden state within our consciousness, right? And I think that's something that GA cannot comprehend in a sense that it feedbacks between your like a Markov blanket wrapping around the entity. So that's how the free energy principle basically focuses on the biology of processes as opposed to the thing itself. So I think that definitely expanded our way of thinking what is fit and what is not, because it takes into the observer itself as part of the system. And I guess in terms of the entropy thing, I actually, it's not a question, but I think it will be an interesting discussion between us, because as Alessandro mentioned, the entropy was largely from the Shannon's definition of entropy, which is the amount of surprises or redundancy in some signals. And actually, Shannon was Wiener's student, like a module student in lecture hall or something. And Wiener commented on Shannon's entropy, basically saying that he agreed with most part except for one part, which is the positive sign, like information equals positive entropy. Wiener said information actually equals to negative entropy. And I think that's one definition that is very much ignored by us nowadays. Because, for instance, Shannon would think that if we report on more likely event, you actually get more information. But Wiener would think that if we report on less likely event, we get more information. And I think that would change how we think about wave function collapse as well. Because, like, what is actually the value in the information that we're compressing? Yeah, because a lot of students at UCL are also using wave function collapse, and a lot of times they only use it as a tool. And that confused them because of the homogeneity, as Alessandro was saying, and also because of voxels. How can you actually ensure connection between same modular units, and then they get stuck? But I think it's more an information problem.
Well, I mean, I'm still not entirely sure about the conversation where we have really drilled down to, because in the paper of Alessandro and Alessio, it talks about spatial qualities and filtering them out in architectural scale, but without actually naming those spatial quality other than the fairly simple qualities of density, which really is difficult to even define as a quality. It's a very obvious thing, and is that a spatial quality or an organizational quality? And we're there in the solar gain energy that you are promoting. Actually, it's not a very extremely linear, and from a data set that is extremely predictable, where no kind of machine learning is required. In fact, you can predict the sun for the next 10,000 years easily. I'm wondering at the moment, and you are actually in the presentation yourself speaking about the relieving the heavy computation of the algorithms in the beginning, where we are not turning in circles there. I'm trying to be very critical because there is a lot of criticism on your approaches, and they're not all solving. So could you elaborate a little bit more on how you would, either or of you, how you would see that your approaches are actively not problem solving, as you said, and not optimizing, but at the same time exactly trying to do that? I mean, both of in Alessandro's and Alessio a little bit less, because I still couldn't find out exactly the goal, because you, apart from what you said about the densities, if the algorithm has, or if the learning has achieved the reinforced learning like the 50 or 70% density or so. So maybe that could, because I'm very excited about it, but at the same time I must put on the brakes to see like how do we satisfy critics of this, and there's many of them.
Should I?
Any or whoever would like to.
I mean, thank you so much for the criticism. It is actually very, very valuable every time we get comments like these. It's true that right now it's very linear, and the AI, the machine learning working on induction is merely basically accelerating or augmenting the problem inherent in the rule-based system. And yeah, so it's like going round and round if we don't have new input. But I guess what we're trying to say is that yes, the sun can be predicted also with AI for the next 1,000 years, but it's then a matter of scale. Like for instance, we can predict the sun on a universe scale, but it's hard to predict user energy demand. And to actually synthesize the two, I think that was the problem space that we try to target with machine learning, or else it will be a waste of actually using AI for a problem that's not needing intelligence.
May I interrupt you there?
Yes,
I usually
please.
don't do this, because particularly when it comes to energy users, they're equally as linear. I mean, like there's the old power plant problem that was well described then, when in the UK people switch on the tea kettle in the morning. And it's extremely periodical and rhythmical how energy is used. So again, in a very, very local context, this might minutely fluctuate, but in a even mid-sized local global context, it's quite easy to predict, and has been since the 50s basically. Otherwise you wouldn't be able to use nuclear power plant.
Then I guess actually we should be braver to put the argument earlier, is that, you know, with the installation that we're proposing, we're actually offering a potential to decentralize energy production. Like we have only been using large centralized systems which are more predictable, but what if everyone actually has the opportunity to generate their own electricity? Then the apartment next door might not have the same capacity because your window is facing a reflective building with a very shiny corner or something. So I also am not sure how much social value it actually has of decentralizing everything, but we feel like if we want to maximize choices in a system, we might take advantage of this. So yeah, I agree. The biggest problem is like how valuable is the whole research itself? Like, does the society actually need it or not?
I didn't go that far.
No,
I did not
but
criticize
it's something that I'm also asking myself constantly. Entropy problem, right? Like, don't waste resources into meaningless. It's what Weiner taught me.
Well, if I can start. Okay, a bit loud. If I can start about the spatial qualities problem, well, we can argue that apart from very simple, purely geometrical and topological qualities, everything that comes next is not just purely a quality of the object itself, but it's more a relational quality. It's an affordance that lies inside the object, but needs another agent, generally a person, for what we are concerned about, generally a person, to realize the spatial quality. So it's not that a quality, but a capacity of the environment to generate some specific conditions in relation with something that is inside. And in this sense, being that relational, it's even difficult when you design something by hand to be sure that everyone that will be there will find that there is this specific quality. Well, even within the realm of more traditional architecture, there is a lot of discussion that can be undergone between the users if there is a specific quality of, or it is not there. And for this specific reason, apart from, geometrical and topological qualities, what comes next is no more a matter of certainty, is no more a solution, but is a question that we open up. And in some sense, it's always an open question. And as I love to state, to some extent, we as architects, we are not creating spatial qualities, but we are more conjuring them as you conjure demons. You try to achieve something, but you cannot be entirely sure what comes out. And for that reason, we can just maybe the final goal is not to have something that for sure grants you that you have this specific quality and that's it, but to expand the reach of what is possible and then try to orient in this complex landscape and find a way to find that. This is my modest answer. It's really difficult to create a machine that creates specific qualities, but it's really possible to create a system between humans and machine that expand the reach of those possibilities and our ability to cognitively explore those landscapes.
Actually reminded me of a small thing. Like in one class, we taught the students to use a GPT-2 and feed it with a lot of philosopher book. And one of the students asked a very, very, let's say, innocent question. It asked the AI, what is the experience of architecture? And I was like, whoa, it's asking the AI without a physical body, what is a physical experience of architecture? And of course, the GPT-2 just answer a bunch of text that has no meaning. But yeah, I feel like this is exactly the affordance. It's perhaps why we would need machine intelligence for affordance.
May I just
yes.
answer again? Yeah. No, it's... on one side, I would like to say that depends on the qualities that you're talking about. On one side, there are the qualities that we chose to translate into quantifiers to train the model. So this is a deliberate choice because we identified those. And in part, it's also probably a window into what would be a possible role of a human designer in interacting with those systems. So you don't design the object, you design the rewards, or you design the quantifiers. It's still a design task. And we are aware that this is a heavily, let's say, the human part of the design. But it's also about training a non-human sensibility to do something. Rather than trying to train something to mimic the user, this is coming back to the cyberneticists. It's actually something that Negroponte wrote. I want a machine that tells me something in contradiction, even with, or gives me something new, that doesn't give me an extension of just my own sensibility. And our intention, I don't know if we actually actualize this statement, but the intention is for sure to get the non-human sensibility to what it does best, in a way, and especially what the human cannot do. Another thing that Alessandro mentioned during the presentation was the difficulty in evaluating these objects, because we have, for example, we have a perceptual limit that it's really hard to analyze three-dimensional objects if we don't dissect them into two-dimensional projections. But a neural network can see in 1,000 dimensions. Easily. See meaning perceive, analyze, process, and elaborate on that. So it's also one of the possibilities to have this kind of, again, non-human sensibilities, because the network that we train judges spaces on its own accord. And that's a non-human kind of way of judging, or let's say train a sensibility for certain qualities rather than others that are different from the qualities that we might judge in a space. So the goal is not to, let's say, predict the qualities of that space, but actually to have the possibility to explore certain configuration that in general we would not be doing in the first place. I would like to also quote something, because we also come to this from the perspective of how artists build machines to do something. And for instance, Richard Serra was one of the reference points. At some point, he elaborates on his own artistic path. So it stops painting because he sees a painting by El Greco where Las Meninas, not El Greco, but Las Meninas, where actually the artist makes the Velázquez, yes. Exactly. I always confuse the two, but where the artist makes the observance the part of the painting, and it does that in the 16th century. So he says, what am I painting for? So it starts again with a list of verbs, a list of actions, a list of materials. So he builds basically an abstract machine that relentlessly put this to use. So does Pollock, so does a lot of other artists. They build machines to get into this non-human kind of process and let the machine run its sensibility relentlessly until it brings them to places where they would not naturally go.
I think we can leave it with that. Is there any last question in the audience? Well, then I'd like to thank all of you for your very insightful and very honest answers and very critical discourse that we started here. It could go on for much longer, very easily, but I'm closing the session here now. It's 5:15 in Hong Kong. Thank you all, and I hope you continue to enjoy the symposium. Thank you very much.
Thank you.
Thank you.
So nice to meet you all.
Yeah, likewise.
Instagram. I'll see you there.
Yeah. Sure. Thank you, Tobias. Nice questions. I love it.
Pleasure. Bye-bye.
Bye.